Okay, good morning, everybody. So we're on the last major data structure in this course. So today's lecture is on singly linked lists. So we're going to do the same thing that we did for the array-based list. We're going to implement one of these things, and then we're going to implement an iterator for a singly linked list as well. All right, so a linked list is an implementation of a list. So it supports all of the operations that the list interface supports. Instead of using an array to store the elements, it stores the elements in a linked sequence of nodes. Right? So it's similar to a linked stack or a linked queue, right? In that it's a linear sequence of nodes. So in a list, the front node is traditionally called the head node, and the node at the end of the list is traditionally called the tail node. In a singly linked list, every node has a link to the next node in the sequence. So just like in our linked stack and linked queue implementations. There are many variations of linked lists. So you'll see probably the most common one is the doubly linked list. So in a doubly linked list, every node has a link to the next node and to the previous node in the sequence. And that's the way that the Java standard library class linked list works. So it's a doubly linked list class. So if you ever use Java util.linked list, you end up with one of these. Okay, so if you want to see what a linked list looks like in a picture, it looks a lot like a stack or a queue, right? So here's our list, a linked list of size 3. Right? So I've got the first node is the head node, right? And the last node is called the tail node, right? We know that this is the last node because its next link is null, right? So there's no more nodes after the tail node, right? If you have one of these things, right, then to get to any node in the middle of the sequence, right, you have to start from the head node, right? So we don't have an array or some other collection of nodes, right? All we're going to have is a reference to the head node. So to get to an element in the middle of the list, you start at the head, and then you have to follow the links until you get to the node that you want to get to. Right? And so because of the way that the linked list works, if you want to get or set an element by index, right, then that operation has time big O of n, right? Because you have to follow a bunch of links to get to that node. And compare that to an array-based list where getting or setting an element by index is O1. Right? And so for that reason, a linked list is typically much less common to use than an array-based list. Right? Normally in a list, your most commonly used operations are getting or setting an element by index or adding an element to the list at the end. Right? And so a linked list is not good at most indexed-based operations. Or it's not that it's not good, it's slower compared to the array-based list. Okay, so in an empty list, you have no head node or tail node. Right? So for our purposes, we're going to keep two fields. Right? So one for the head node and a second reference for the tail node. In the empty list, both of these references are null. Right? So there is no tail node, there is no head node. So the structure of a linked list, you can think of it as being recursive, right? Just like in a stack or a linked stack or a linked queue. Right? You can think of every node of the linked list as being the head node of a smaller list. Right? So the head node for the list of size 4 is just the head node of the list. Right? If you consider the second node of the list, right, then that's the head node of a list of size 3. Right? And if you consider the third node of the list, that's the head node of a list of size 2. Right? And of course, the last node is a head node of a list of size 1. Right? And because the structure of the list is recursive, it's very easy to write recursive algorithms using a linked list. Right? You don't normally write them recursively. Normally, you would write linked list algorithms using iteration. Right? So start at the head node or start at some node and just move some number of links until you get to the node that you want to get to. But you can, if you want to, write them recursively. I guess in the classroom setting, professors like to ask you questions like this. Right? In some interview settings, the interviewers like to ask you questions like this. Right? Oh, wait, where's my algorithm? Here, okay. So the structure is recursive. It's easy to write recursive algorithms because you just translate the algorithm, or you just write the algorithm to exploit the recursive nature of the list. right? So if I wanted to compute the size of a list, you can do that recursively. You can also do it iteratively, right? So if I wanted to compute the size of this list here, right, you just start at the head node, you set a counter equal to 0, and then you just start to follow links, right? So I'm at this node, so that's one node. Follow the link, that's 2 nodes. Follow the link, that's 3 nodes. Follow the link, that's 4 nodes, right? So it's easy to do this iteratively. Recursively, it's also easy to do, right? So if I wanted to implement the size computationally, right? So in other words, if I wanted to write an algorithm to compute the size, right? I can call a recursive helper method, the recursive helper method. So recursive size here computes the size of a list given its head node. Right? Now remember, you can think of any node in the list as being the head of a list. So this is easy to write recursively. Right? If your head node is null, there's no nodes, so your size is 0. Right? If the head node is not null, then there's at least one node. Right? So that's going to be 1, right? Plus the number of the number of nodes in the rest of the list, right? Or the size of the rest of the list. Right? What's the rest? Where does the rest of the list start at? It starts at the next node relative to the head node. Right? So you just call recursive size recursively, and away you go, and that computes the size of the list recursively. And you can basically convert any iterative algorithm on a linked list to a recursive version. It's not hard to do. All right, so let's actually implement one of these classes. So we're going to implement slinked list, right? So remember, slist is our simplified list interface. So slinked list is the linked list class that implements that interface. The nodes for a singly linked list are exactly the same as the nodes for a stack or a queue, so we're going to reuse that class. I'm not going to make the node class private. I'm going to make it package private. And so that is so that other classes in the same package can access the node class directly by name. And the reason I'm going to do that is because we're going to split the implementation of our linked list class into the linked list, and then we're going to have some algorithms that also work on linked lists in a separate class. Right, so we want that other class to have access to the nodes, otherwise there's no way to operate on the structure of the linked list. Right, so we're also going to have some package private methods that return the head node, the tail node, and a node by index. Okay, so here's our class. Right, it's generic, right? So we need our generic type here. It implements the slist interface, which is also generic, right? So we need that generic type there. Internally, there's a static class called node, right? So these are the nodes of our linked list, right? It's exactly the same as for linked stack or linked queue. It's a static class, remember? So nodes can exist independently of linked list objects. We're going to keep track of the size. So you can compute the size of a linked list every time. That's, it's expensive to do. You have to look at every node in the sequence, which is O(n), right? So instead, I'm going to keep track of the size or the number of nodes in the list. We're going to have a reference to the head node of the list, right? So the node, remember, is generic. So it's node E, right? And we'll have a reference to the tail node. You technically don't need this reference here, right? Because you can always get to the tail node starting from the head node, right? Just follow all the links until you get to a node whose next link is null. But again, that takes time, big O(n), and so it's much more efficient just to keep a reference to the tail node. Right? Now what you don't want to do is you don't want to keep a reference to every other node in the list, right? Because then you might as well just make an array-based list. Okay, so package private method that returns the head node, package private method that returns the tail node, right? These aren't necessary. I'm just putting these in so that our utility class that's going to operate on linked lists has access to the head and tail node. Okay, every list should, every class should have a constructor. So here we've only got one. It's relatively easy to implement the other constructors, right? So our default or no argument constructor makes an empty list or initializes an empty list, right? So an empty list, its size is 0, right? The head node is null and the tail node is also null, right? No head node, no tail node. Size is dead easy, right? You just return the size of the list, which we're keeping track of. Right? Okay, now what about adding to the end of the list, right? So that's exactly like in queuing, an element into a queue. Right? Notice here that I am telling you that the enqueue implementation in the lecture slides has an unnecessary special case. Right? So this is, you can reuse what I'm going to show you for the queue as well. Okay, so there is one special case when you add to the end of a list. Right? So when you add to the end of an empty list, right, you have to set both the head and tail fields of the list. Right? Normally when you add to a list and the list is not empty, you're only adjusting the tail node. Right? Because everything happens at the end of the list. In the case where you have an empty list, you also have to update the head node as well. Right? So if you want to add to the end of an empty list, to a non-empty list, right, then what you need to do is you need to make a new node, right, to store the new element. Right? So there's my new node. Right? Once you've got your new node, you want to hook up the old tail node so that it points to or refers to the new node that you just created. Right? So I want to do that. Right? So I want to adjust this tail so that it's equal to n. Right? And then I want to increase the size of the list by 1 because I just added a new node to the list. And then finally, n's your new tail node. So you have to you have to update your tail node so that it's now equal to n. Right? Like that. And there's your list of size 4 now. Right? So it's pretty easy to do. Right? So to add an element to the end of the list, you make a new node. Right? In the node, you're going to store the element. Right? That node's next link is null. Right? Because it's the new end of the list. Right? So it doesn't refer to any other element. If the size of the list is 0, I need to update the head node. Right? So now there's a head node, and that head node is n. Right? If the size of the list is not 0, I need to update where the tail node points to. Right? So this tail next now refers to n. Right? Finally, the last two steps. Right? I've got a new tail node, so update the reference to the tail. Right? So this tail is equal to the new node. And then update the size of the list. So increase the size of the list by 1. That's very easy to forget to do. So don't forget to do that. Okay, so what about getting and setting by index, or removing by index, or doing anything else by index? Right? And so in a linked list, the problem is you can't, you don't have direct access to the node at index n, right, or whatever I, right? So if you want to perform some operation that uses an index, then you have to start at the head node and move to the node that you want, right? And that's because we only have a reference to the head node. Right? Except in the case where you're doing something at the end of the list, because we also have a reference to the tail node. Right? Now, in every method that uses an index, you could write the loop that moves a node, that moves you to that node, but it's much easier to write a method to do that for you and just reuse the method. Right? Similarly, in a list, we're always worried, are the indexes valid? So it's useful to write a method to validate the index as well. So away we go. Right? So a method, package private method called validate, right, throws an exception if the index is not valid for this list. Right? So if the index is less than 0, or if it's greater than or equal to the size of this list, we just throw an exception. Okay, so the method that gives you a node at that index is called move_to. Right? Now, this method is not meant to be used by regular users of the class. Right? So people who are using a linked list class, they don't actually need to know or they don't need access to the nodes of the list directly. Right? All they really care about is, can they get access to the elements? Right? And so this method is not public. Right? It's package private so that our utility class can also move to a given node. Right? So move_to moves to an index. No, because it's package private, I'm not going to do any validation here. Right? So this method is not meant to be used by general users. Right? It's meant to be used by people or programmers who know what they're doing. Right? And so I'm not going to validate this index here. I'm just going to assume it's valid. So when you're using this method inside the class, it's up to you to make sure that you're calling this method correctly. Right? There's no index checking here. All right, so to move to a node, there is a special case. Right? If I want to move to the last node of the list, that's just the tail node. So instead of following all the links to the tail node, you can just return this .tail. Otherwise, you just start at the head node, and now you just follow links, right? So starting at the head node, I'm going to write a little loop that runs that many times, right? Each time through the loop, I'm just going to advance n one node forward, right? So if you're at node n, to get to the next node, that's just n.next, right? And so at the end, after the loop finishes running, you're at the node at that index, right? So if you want the node at index 0, that loop runs 0 times, right? So n is equal to this dot head. If you want the loop at the node at index 1, this loop runs exactly once. So starting at the head, you go to this dot head dot next. That's the node at index 1, right? And so on and so on and so forth, right? And so at the end of this, so this method successfully turns the node at that index, right? And once you have a node at that index, now you can do something with that node. Like, oh, here's the recursive version of move to, right? So if you wanted to do this recursively, there's no reason to do this other than for academic reasons, right? You write a little recursive helper method, right? So the recursive helper method moves to a node at that index, starting at this node here, right? So if I want to move to, so this index is relative to the that node n, right? So if that index is 0, you're already at node n, so you just return n, right? If that index is greater than 0, you need to move some number of links. Well, you need to move that number of links to the right, right? So I'm going to move one node to the right, and then move index minus 1 more nodes to the right, right? So n.next is the node to the right of n, right? Then I need to move that many more nodes to get to the node that I'm looking for, right? And so that method just recursively calls itself until the index becomes 0, and then you're at the node that you want. Okay, so given move to, right, get and set are trivial now, right? I just move to a node and return the element at that node, or change the element in that node, right? Move to is in on because you might have to follow up to n minus 2 links in the worst case, right? So to get to the second last node in the sequence, I have to follow n minus 2 links, right? And so move to, and that means get and set, or any other method that operates by index, is in on. Okay, so get. I have to, so this method is meant to be used by other people, so it's public, right? So because other people are trying to use this method, it's useful to validate the index to make sure they're not trying to do something silly, right? So validate the index using our validate method. Assuming you get past the validation, just move to the node that you want to go to, right? And then return the element in that node, right? So super easy once you have move to. Set is similar, right? Again, other people are supposed to, other programmers are going to be using this method, so it's public, right? Validate the index, move to the node. Now set normally, so set is the method that overwrites an element. Normally it returns the element that it overwrote, right? So remember the element that you overwrote, right? So that's just NELEM, right? Then go ahead and update NELEM so that it refers to the new element, and then return the old element that you just overwrote, right? So set's also easy. Notice though that it's, although it's easy, it's a lot more complicated than the get and set methods in the array-based list, right? In the array-based list, you just index into the array and away you go. Okay, so where the linked list outperforms an array-based list is when you want to do something at the front of the list. So if you want to insert or remove at the front of the list, linked list is much faster than an array-based list, right? So inserting an element at the front of an array-based list means that the list has to move all of its elements one position to the right. That's ON for an array-based list. For a linked list, you just make a new node and stick it on the front, and that's it, right? So it's identical to pushing an element onto the top of a node-based stack, right? And we saw that push and pop for node-based stacks are in both those methods are in O1. Okay, so to add a new node, to add a new element to the front of this list of size 4, right? What you're going to do is you're going to make a new node, right? So there's my new node, right? You're going to hook it up to the current front head of the list, right? And then you're going to adjust the head of the list so that it refers to the new node, right? And then add 1 to the size of the list. Right. So to add to the front of the list, I think there's something missing here. We'll figure it out in a second. I'm going to make a new node, right? So that's to add. Right. Here I'm making I'm setting the element of the node, but I'm not setting the next link. Right. I'm going to do that on the next line. So to add next just refers to the head node, the current head node. Right. Update the head node so that it refers to the new node. Increase the size of the list by 1, and there's a special case missing. Right. So anybody see what the special case is? There is a special case that's missing from add front. Yeah.
You have to adjust the tail if it's an empty list.
That's right. Right. So when you're implementing the linked list this way, where you're keeping track of the head and or tail node, there's almost always a special case when you're doing something with the empty list. Right. So when you add to the empty list, I also have to update the tail node. Right. So this tail is now equal to add. Right. So in here, well, let me just edit the slide. Right. And it's very easy when you're implementing these data structures. Not just lists and stacks and queues, all sorts of data structures. In many cases, when the data structure is empty or only has one thing in it, there's often a special case to deal with that. So if this size equals 0, this tail equals to add, like that. Whoa, like that. Oh. Right. You could also do it after updating the size. So if this size equals 1, this tail equals to add, but it doesn't matter, right? You have to update the tail node if you're adding to the end of an empty list. All right, so the other place where a linked list outperforms an array-based list is if you are at a node, right? So suppose I happen to be at node 1, or I happen to have a reference to node 1, and I would like to insert a new node after node 1. Right? So if I want to insert the 4 after the 1, and I happen to have a reference to this node, I can do this in O1 time. Right? Because all I need to do is make a new node and then update some links. Right? Now, if you want to insert into the middle of the list, but you don't have a reference to the node in front of it, it's still ON. So just like an array-based list. Right? But remember, inserting or removing at an index, if you have the node in front of it, is potentially more efficient than in an array-based list. Right? So if I want to insert an element at index I, so here I want to insert at index 2, right? Then I have to adjust the next link of the node in front of it. Right? So I need to adjust the node of the next link of the node in front of the point where I'm inserting at. Right? So the idea here is, right, you move to the node in front of the one you want to insert at. Right? So here I'm going to move to the second node in the sequence. Right? We're going to call that node n. Right? I'm going to make a new node. Right? So here's the node where I'm going to insert. Right? So it's going to hold the 4. I'm calling this to add. Right? So there's my new node. Right? Now what do I need to do? Right? So I'm going to need the node after the node n, right? Because I need to hook up to add to after, and I need to hook n up to add. Right? So I need to remember what is the after node, or I need to be able to get the after node. Right? Okay, so now you can see why I've done this. I've written it this way, right? To get to after, I need n, right? Because I need n.next to get to after. If the next step is changing n.next, then I no longer can get to after, right? So I need to remember what after is before adjusting n.next, right? I adjust n.next so that it points to or refers to the element that I'm inserting, right? Now I can take the element that I'm inserting and take its node and make it refer to after, like that, right? And that effectively inserts an element into the list, right? But notice the steps that are required. Right? Once you get to the node, right, make a node, remember a link, adjust the link, adjust the link, right? So there's a constant number of operations to insert a new node, assuming you have the node in front of it, right? And then, of course, don't forget to increase the size of the list by 1, and you're done. Right? So if you follow the picture, you can easily translate that into code. Right? So I'm going to have a special case here, though. So if I want to add at the end of the list, so remember this method, the add or insert method here. In Java, the Java standard library version of list lets you add at the end of the list. So in other words, you can specify an index that's equal to the size of the list. Right? Our validate method doesn't like an index that's equal to the size, so we check that case first. Right? So if the index is equal to the size of the list, just add to the end of the list, right? Using our other add method, and then you're done. Don't forget the return statement. If you forget the return statement, you end up adding the element twice. Right? Okay, so if you're not adding to the end of the list, validate the index. Right? Now, I have a special case here. So I have a method called add front that adds to the front of the list. The reason I have a special case here is because of this move to method. Right? So move to moves to, I need to move to the index, to the element in front of the node I want to insert at. Right? So if I want to insert at the front, index is 0. Right? And so I end up trying to move to a node whose index is -1, which doesn't exist. Right? So I need the special case here. If the index is 0, I'm gonna call a special method to add to the front of the list. Right? Otherwise, just move to the node in front of the one where you want to insert at. Right? Make your new node. Right? Store the element in the node. Right? Instead of remembering what n.next is, I'm just going to use it right here. Right? So remember, store the element in the node. Make your new node next link. Point to the node after n. Right? Then adjust n next to refer to the new node, right? And then increase the size of the list by 1. Right? So those steps right there are just the picture here, right? Move to the node n, make your new node, right? Find the node after n, which is n.next, right? Make n point to the new node, and make your new node point to n next. Right? And so that's just that part right there. Okay, so what about add front? Did we do add front? Where's add front? We didn't do add front yet, did we? Oh, we did. It's right here. So there's add front, right? Okay, so what about removing an element from the front of the list? Right? So compared to an array-based list, this has complexity 01 because all you have to do is remove the front node of the list, right? And that's exactly like dequeuing an element from a node-based queue. Right? So to remove the element at the front of the list, right, I'm going to attain a reference to the current head node, but we already have that. That's just this .head. Right? I want to adjust the head node so that it refers to the next element in the list. Right? Decrease the size of the list by 1, and then return the element that was removed. Right? Once again, where's the special case? Notice there is a special case, so we'll get to that in a second. Right? I guess this is technically a special case, so if this list is empty, you can't remove the front element. Right? Otherwise, get the node to remove, right? So that's just this .head. Right? Update this .head, right? So this .head is just this .head.next, right? Or to remove .next, it doesn't matter. Right? Now you do have a special case here, right? So if you're going to remove an element from the front, normally you only adjust the head node. However, there's a special case where if you remove the front element from a list of size 1, you now have an empty list. So you have to adjust the tail node in the special case. Right? So if the current size of the list is 1, right, you're going to remove that front element, which is also the last element. So you have to adjust the tail node. Right? This .tail is now null. Decrease the size of the list by 1, and then return the element that you just removed. Again, if you just count the number of operations here, right, you'll see that there's nothing here that depends on the size of the list. So the complexity of the algorithm is in big O of 1. Oop. Okay, so what about removing by index? Right, so removing by index is similar to inserting by index. Right, I need to move, if I want to remove that 2, right, I need to adjust that link here. Right, so I need to adjust the link for the node in front of the element that I'm removing. So I need to move to the 1, and then I need to make that 1's next link refer to the node after the one I'm removing. Right, so in a pictures, the way it looks is as follows. Right, move to the node in front of the one you'd like to remove. Right, we're just going to use move to. Right. Remember, what is the node that you're going to remove? Right, that's just n.next. Right. Remember what the node is after the node that you're going to remove, because I need to link n up to that one. Right, so that's just n.next.next or to remove.next, however you want to write it, it doesn't matter. Right. Unhook the node that I'm removing. Right. Now, it's important that you unhook this node. Right. So if you don't unhook the node, then what ends up happening in Java is you've got a node that has a reference to the after node. Right. And so if you actually remove the after node from the list at some other point, and you forget to unhook this reference here, the Java virtual machine can't get rid of the memory for the node because there's some other node still kicking around that has a reference to after. Right? So you have to remove that node. So you have to null that link. Right? And then I'm going to set n so that it refers to the after node. Right? And then finally, decrease the size of the list by 1 and return the removed element. So again, if the index is 0, there's a special case here which I have already implemented, right, with remove front. So just call remove front. Right. Otherwise, validate the index. Right. Move to the node at in front of the one you want to remove. Right. And now I'm going to call this method called remove after. Right. So instead of inserting the code for removing the node here, I'm going to make a separate method that can remove a node that's after some specified node. The reason I want to do this is because in our Iterator class, right, the Iterator class also has a remove method. Right? In the Iterator class, the iterator is pointing at a node. Right? And so if the iterator is pointing at a node, it can easily remove the node after it if you have a remove after method. Right? If you don't have remove after, the iterator is stuck calling this version of remove. Right? And this version of remove moves to an index has to move to an index. Right? So that becomes big O of n. If you have remove after, the iterator remove method becomes big O1. Okay, so remove after is just the pictures in the slide. Right? So let's go back quickly. Right? So we've already moved to node n, so now I'm going to call remove after. Right? So remove after remembers what that node is. Right? It then remembers what that node is. It then unhooks the first node and then hooks up the node in front of the one you just removed to the one after. Oops, sorry. Okay, so remove after. We're going to remove the node after the node n. Right? So the node I want to remove is just n.next. Right? The node after the one I'm removing is n.next.next or to remove.next. Right? Either one's fine. Right? Okay, I want to unhook the node that I'm removing from the next node in the sequence. So to remove.next is null. Right? I want to hook up n to point to the node after the one I'm removing. So n.next is after. Right? Now, we've taken care of the special case where you're removing the front node. Right? But there's now a special case where you're removing the last node. Right? So if this node after is null, right, then we have then the node you just removed was the tail node. Right? If you remove the tail node, you have to adjust it. Right? So if you remove the tail node, what is the new tail node? It's the one that's in front of the tail node, but that happens to be n. Right? So adjust the tail node so that it now refers to n. Decrease the size of the list by 1. Return the element that you removed. and there's how you remove a node from the middle of a list. All right, so there's 15 minutes left, so I guess we'll go on to the next set of slides. Okay, any questions so far? Yes? Does it actually delete? No, that's a good question. So let's go back to the slides. So the funny thing in Java is that as a programmer, you never care about whether or not something is actually getting removed from memory, right? The Java virtual machine takes care of that for you. So let's look in the picture here and see what's going on. Right? So I guess the first thing to remember is that the virtual machine can remove an object from memory if there's no references to that object. Right? Okay, so in this picture here, what references do we have? We have a reference head, right? That points at the head node. Right? We've got a reference tail that points at the tail node. Right? And so head or tail, those nodes will not be removed by the virtual machine. Right? There's a reference to those nodes. Right? This is the node I want to get rid of. Right? So who has a reference to remove? Right? Well, n has a reference to remove. Right? That's n.next. Right? So as soon as I adjust n.next to refer to something else, right, to remove can go away. And so that lets us take care of that. So that answers your question, right? There's no other, in a correctly implemented linked list, nothing else has a reference to remove, right? If you have, in an incorrectly implemented linked list, something might have a reference to remove, right? But if you correctly implemented it, as soon as you unhook n, to remove can go away. Okay, implementing it, oh, not that one slide. Implementing an iterator for a linked list. All right, so just like for an array-based list, the way that you should think about an iterator is that it sits between elements, right? So this iterator shown in red sits between the elements C and D, right? And so this is sitting between the indexes 2 and 3, right? Now, in a linked list, you really don't want to keep track of indexes, right? Because the only way to get to a node by index is to start from the head node, right? So instead of keeping track of the indexes 2 and 3, I'm going to keep track of references to nodes, right? Now it's a little bit different in a linked list than in an array-based list, and we'll see why in a shortly. Right? Okay, so if this iterator is sitting here, and you call next on that iterator, right? And then what the iterator is supposed to do is it's supposed to return the node immediately, the element in the node immediately before the iterator, right? So calling next on this iterator should return the C, and it should move the iterator one position to the right. Right? Now, that means this iterator needs to keep track of the node in front of it. Right? Does the iterator need to keep track of the node after it? The answer is no, right? Because if you're keeping track of this node, you know what the node after it is. You just follow that node's next link, right? Now remember what remove is supposed to do, right? So if I call next on this node, sorry, on this iterator, it's going to return the C. If I call remove after calling next, it's supposed to remove the C. Right? Now, what do I need to do in order to remove the C? Well, I need the node in front of it. Right? And so this iterator is going to keep track of that node and the node in front of it. Right? I want to keep track of this node here so that I can efficiently remove that node that was just returned by next. So instead of keeping track of previous and next, like we did for the for the array-based list, we're going to keep track of the previous node and the node in front of it. So I'm calling that previous because I couldn't think of a better name. Right? So that's previous. Right? So previous is the node that's going to be removed when calling the iterator's remove method. Right? If I want to remove that node, then I need the node in front of it, right? For remove after. Okay, so inside our S linked list class, we have an iterator method. Right? The iterator method returns a linked list iterator, so LL iterator. Right? So just like with the array-based lists, we're going to have a nested inner class that represents the iterator. Right? Our iterator holds the previous node, right, and the node in front of the previous node. Right? So that's previous, previous. Okay, so at the start of the iteration, right, there's obviously no previous node. Right? Now, when you start to implement the iterator class, if you actually implement it this way, so if you actually set previous to null, you're going to fairly quickly realize that you're always worrying about there's some special case. Right? So you're always dealing with the special case where previous, you're always checking is previous not null, because you're going to be using previous to move to the next node. Right? And so I want to avoid doing that if I can. Right? So what I'm going to do is I'm going to silently insert an unused node. Right? Now this is funny. So the linked list class doesn't even know that this node is here. Right? The only class that knows that this node is here is the iterator class. Right? So the iterator class is going to insert a new node. Right? So our constructor is going to silently make a new node. That node holds no element. Right? So there's no value stored in the node. Its only purpose is to ensure that previous is never null. Right? So I'm going to make a new node, store no element in it. I'm going to hook it up to the head of the linked list. Now, previous, that can still be null, right? So I don't care so much about that, right? But I don't want to deal with the special case of previous being null all the time, right? So if we go back now and look at the constructor, right? So our iterator constructor, it makes a new node, right? Stores no element in the node, but hooks that node up to the current head of the list. Right? Now remember, this is an inner nested class, so it has access to the head node of the linked list. Right? And again, remember, how do you get access to it? Well, it's slinkedList.this. Whatever the name of the field is. Right? Previous can be null, so that's fine. We'll go ahead and do that. Right? So this is called the sentinel node. Now you can also implement the linked list itself so that the linked list has a sentinel node at the front. You can also insert a sentinel node at the back, right? And so the empty linked list in that case would have two nodes, right? The node at the sentinel node in front, the sentinel node in back. If you implement it that way, you don't have to worry about the special cases anymore, right? Because in the empty list, there's always a node at the front and there's always a node at the back, right? So there is a way to implement linked lists using these sentinel nodes. It's debatable whether or not that saves you a huge amount of work, but it is useful to make sure that you never have to deal with the special cases. All right, has next. Right, so has next returns true if there are more elements to visit. Right, now how do I know if there are more elements to visit? Right, so I've got this previous node here. Right? Then if there is another node to visit, right, then previous.next, right, is going to point to some node. Right? So in other words, previous.next will not be null. Right? So when I start the iteration, right, previous.next points to the current head node, so it's not null. If you iterate till the end of the list, right, so here's my iterator now, right, now previous.next is null. Right? And so now I know that has next must be false. Right? There are no more elements to visit in the sequence. Right? So I can use that condition right there for has next. So has next is one line. Right? As long as the previous element that we visited has another element, then there is a next node. Okay, so what does next do? So next advances previous and previous one position to the right, and then returns the element that was in previous. So if my iterator is sitting here, right? And we call next, right? The iterator moves. Sorry, what am I doing here? Next is supposed to return. Oh, right. So the iterator is supposed to return next. If I call next, it moves one position to the right, and then returns the element sitting in previous. Okay, so what does next do? First, you have to make sure there is actually a next node or a next element, right? So if has next is false, throw an exception, right? Now just advance both pointers, both references forward, right? So to move these two references forward, previous just becomes equal to previous, right? Previous just becomes equal to previous.next, right? Like that. Don't reverse the order, right? So the order here is crucial, right? If you reverse the order, then you end up doing the wrong thing, right? Because previous depends on the current value of previous, right? So you have to make sure you update this one first, then update previous, right? Now you can return the element that you just iterated over. Okay, what about remove? So removing any element except the element in the head node, you can do that using remove after, right? So that was why we went through the trouble of implementing that separate method remove after inside of our linked list class, right? It's easy to do if you're in the iterator because the iterator has previous, right? Or sorry, it has previous, right? So all you have to do is call remove after on that node there, right? And that will remove the C in this example. Okay, so after you remove the node, what you end up with is the following situation, right? So we just got rid of the previous node. So previous gets hooked up to the next node in the sequence, right? All right, now, previous is supposed to refer to the node immediately in front of the iterator, right? So it's supposed to refer to, it should refer to that node now, right? So assign previous to previous, right? And now, what do we do with previous, right? So if I'm here, there's no way that I can easily get to the node in front of previous, right? Because I can't go backwards in this sequence, right? I'd have to start at the front and come forward in the list again, right? So instead, what we're going to do is we're going to set it to null. Now, this is useful for two reasons, right? So reason number one, this is useful for another reason, right? That reason is the way the iterators work is you can only call remove once for every call to next, right? So if we call remove, I need to remember some way, I need some way to remember that we've called remove and we need to call next again, right? And so the way we're going to do that is to look at the value of previous, right? If that thing's null, there is no element to remove, and we'll throw an exception when we try to remove. Right? So assigning previous to null also tells us that remove has been called once for the most recent call to next. Yes? Oh, sorry, never mind. I thought I saw a hand up. Okay. So if next has been called exactly once for an iterator, then the iterator has the following state. Right? So in other words, if you're at the front of the list, right, with the iterator and you call next, right, previous now points at the head node, right, previous points at the sentinel node. Calling remove front on the list causes the list to adjust the head node, right? So if I try to remove this node, right, I'm going to use using remove front, right? Then the linked list changes the head node so that it points at the next node in the sequence, right? Previous still refers to the old head node. Previous refers to the sentinel node, right? So that's not what I want, right? So what I want to do is we want to set the element in the node referred to by previous to null. So I want to convert that node there to the new sentinel node. And then I want to get rid of the old sentinel node, right? So I can convert that to a new sentinel node just by setting its element to null, right? I can get rid of the old sentinel node just by setting previous to null, right? And when I do that, that also indicates that remove has been called, right? And so your code for remove looks as follows. Sorry, what time is it? Oh, we should go. I guess we'll wrap this up in the next class. All right, everybody, have a good weekend.